January 23rd, 1943. Sidi Bou Zid, Tunisia. The morning sun cast long shadows across the desert as American reconnaissance units reported movement to the west. Large tracked vehicles, heavier than anything previously encountered. Intelligence officers scrambled to confirm what forward observers were reporting. Germany had deployed Tiger tanks to North Africa. For months, Allied intelligence had compiled fragmentary reports about a new German heavy tank. Reports from the Eastern Front described a massive vehicle mounting an 88mm gun. Soviet intelligence shared photographs of destroyed 34 tanks, their armor punched through by weapons of unprecedented power. British forces in Tunisia had encountered mysterious new German armor that shrugged off hits from 6-pounder anti-tank guns. Now, American forces would face this weapon directly. The Tiger I represented Germany's response to the realization that existing medium tanks could not guarantee battlefield dominance against Soviet armor. Development began in 1941 when the German Army Weapons Department issued specifications for a breakthrough tank. The design needed to mount the legendary 88mm anti-aircraft gun, the same weapon that had proven devastatingly effective in anti-tank roles during the French campaign and in North Africa. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The tank needed armor thick enough to defeat all known anti-tank weapons. It needed to inspire fear in enemy tank crews while providing German infantry with invincible support. Henschel und Sohn of Kassel won the development contract in 1941, beating out proposals from Porsche and other manufacturers. Production began in August 1942 at the Henschel factory. By January 1943, approximately 100 Tigers had been delivered to German units. The first Tigers deployed to Leningrad in September 1942. Additional units received Tigers for operations. In Tunisia, beginning in November 1942, each Tiger cost 250,000 Reichsmarks, nearly double the cost of a Panzer IV, and representing an enormous investment in German industrial capacity. The specifications were genuinely impressive and represented a quantum leap in armoured vehicle design. Combat weight of 54 metric tons made the Tiger the heaviest tank in widespread service. This was not a medium tank pretending to be heavy. This was a purpose-built heavy tank designed to dominate the battlefield through overwhelming firepower and protection. Frontal armor of 100mm mounted vertically on both hull and turret provided protection against virtually every Allied tank gun in service through 1943. Side armor of 80mm was thick enough to resist most anti-tank weapons at combat ranges. Even the Tiger's rear armor at 82mm exceeded the frontal armor of most Allied tanks. The main armament, the 88mm KUK-36 gun, was adapted from the famous Flak-36 anti-aircraft gun that had terrorized Allied tank crews in North Africa. Muzzle velocity of 810 meters per second with armor-piercing ammunition provided penetration capability exceeding any Allied tank gun through 1943. At 1,000 meters range, the gun could penetrate 138 millimeters of armor, sufficient to destroy any Allied tank from any angle. At 2,000 meters, penetration remained adequate to defeat Sherman tanks through frontal armor, while Sherman guns at the same range could barely scratch Tiger armor. This enormous advantage in firepower and protection gave Tigers theoretical capability to engage Allied tanks from ranges where return fire was ineffective. German tank commanders who had fought in lighter Panzer IIIs and Panzer IVs described the Tiger as providing a sense of invulnerability unknown in earlier vehicles. Crew morale was extraordinarily high. These men believed they were driving the finest tank ever built. The Maybach HL 210 P45 engine represented sophisticated German automotive engineering. This water-cooled 12-cylinder gasoline engine displaced 21 litres and produced 650 metric horsepower at 3,000 revolutions per minute. This was a powerful engine by 1943 standards, providing adequate power for the Tiger's massive weight. The power-to-weight ratio of 12 horsepower per ton was lower than medium tanks, but acceptable for a heavy breakthrough vehicle. The engine consumed high-octane gasoline, requiring minimum 74 octane for reliable operation. The transmission was where German engineers made their critical error. The Maybach Olvar OG 4001 2B gearbox provided 8 forward speeds and 4 reverse speeds. This sophisticated transmission was designed to give Tiger commanders exceptional control over their vehicle's movement. The multiple forward gears allowed optimal engine speed selection for various terrain and tactical situations. The 4 reverse speeds provided retreat capability unusual in heavy tanks. German doctrine emphasized aggressive tactics followed by rapid withdrawal. The Tiger transmission was designed to support this doctrine, but the transmission was fundamentally the same design used in the 30-ton Panzer IV, simply scaled up. German engineers had taken a gearbox adequate for a medium tank and expected it to handle the stresses of a 54-ton heavy tank. The gear teeth were larger and stronger, but not proportionally stronger relative to the massive increase in weight and torque. The bearings were upgraded but remained marginal for the loads they would experience. The synchronizers that allowed smooth gear changes were sophisticated but fragile under sustained heavy use. Maximum road speed of 38 km per hour was adequate for a heavy tank, though substantially slower than medium tanks. Cross-country speed of approximately 20 km per hour under favorable conditions gave the Tiger adequate tactical mobility when mechanical reliability permitted. Operational range of 140 km on roads assumed optimal conditions with proper maintenance and careful driving. Cross-country range of approximately 80 km reflected dramatically increased fuel consumption and mechanical stress of off-road movement. Fuel capacity of 540 litres required frequent refueling during sustained operations, creating logistics demands that German supply systems in Tunisia struggled to meet. Road fuel consumption of 3.8 litres per kilometre meant that a 100-kilometre road march consumed 380 litres, more than 70% of total fuel capacity. Cross-country consumption of 6.7 litres per kilometre meant that cross-country movement consumed the entire fuel load in approximately 80 kilometres, exactly matching the specified cross-country range. The Tiger's combat debut in Tunisia during January 1943 initially confirmed German expectations. On January 20th, elements of Schwer Panzer Abteilung 501 engaged American forces near Robar. Tigers advancing in the morning fog surprised American tank destroyers and infantry positions. The Tiger's thick armor defeated hits from American 37mm anti-tank guns at point-blank range. Shells simply bounced off the sloped glacis plate and turret front. American crews watched in horror as their weapons proved completely ineffective. The Tigers methodically destroyed American defensive positions. The 88mm gun fired with devastating accuracy. Each hit penetrated American armor, causing catastrophic internal damage. M3 Stuart light tanks were destroyed with single shots. M3 Lee medium tanks, the most powerful American armor in Tunisia, were knocked out at ranges exceeding 1,000 meters. American tank crews had no effective response. Their guns could not penetrate Tiger armor. Their tanks could not outrun the Tiger's high-velocity shells. Retreat became the only option. German propaganda celebrated the Tiger's debut with characteristic hyperbole. Newsreels showed Tigers crushing through defensive positions. Radio broadcasts proclaimed German technical superiority restored. Tank crews were told they were invincible. The psychological impact on German forces was immense. After months of fighting in North Africa against British armour, facing increasing Allied numerical superiority, the Tiger seemed like the weapon that would guarantee victory. But within 2 weeks of combat operations, the first mechanical problems appeared. Tigers that had performed flawlessly during brief training exercises began experiencing transmission failures during sustained combat operations. Gearboxes, overheated after prolonged movement. Gear teeth stripped under the stress of accelerating 54 tons repeatedly. Synchronizers wore out, making gear changes difficult or impossible. German maintenance units, already stretched thin, supporting conventional tanks, lacked the specialized knowledge and spare parts to repair Tigers quickly. By February 1943, Schwerpanzerabteilung 501 reported that of 9 Tigers deployed to Tunisia, only 3 remained operational. 6 were undergoing maintenance for various mechanical problems, most related to transmission failures. This represented a 67% breakdown rate after less than 1 month of combat operations. German commanders expressed concern in after-action reports, but attributed the problems to inadequate crew training and the challenges of operating in desert conditions. The pattern established in Tunisia repeated as Tigers deployed to other theatres. Operational availability rates, the percentage of tanks actually available for combat rather than undergoing maintenance, averaged between 50 and 60% throughout 1943 and 1944. German records show that Tiger battalions nominally equipped with 45 tanks could expect approximately 25 to 30 tanks operational on any given day. The remaining 15 to 20 tanks were either undergoing maintenance, awaiting spare parts, or disabled in forward areas awaiting recovery. American forces captured their first Tiger in Tunisia on April 21, 1943, near Mejez el Bab. The tank, No. 251 from Schwerpanzerabteilung 504, had been abandoned by its crew after becoming immobilized in soft ground. The crew attempted to destroy the tank before withdrawing, but American infantry arrived before demolition was complete. The Tiger was recovered largely intact, with damage limited to the main gun breech, which had been destroyed with a demolition charge. American ordnance units immediately recognized the intelligence value of an intact Tiger. This was the first opportunity to examine Germany's most powerful tank in detail. Engineers from 1st Armored Division conducted preliminary examination in Tunisia, documenting external dimensions, armor thickness, and overall layout. Detailed technical analysis would require more comprehensive testing than field conditions permitted. The decision was made to ship the captured Tiger to the United States for complete evaluation. The tank was transported to the port of Bizerte, loaded onto a Liberty ship, and shipped across the Atlantic. It arrived at the Norfolk Naval Yard in Virginia in July 1943. From there, it was transported by rail to the Aberdeen Proving Ground in Maryland. Aberdeen Proving Ground served as the United States Army's primary facility for testing weapons, vehicles, and ammunition. The Ordnance Department maintained extensive testing facilities, including armor test ranges, automotive test tracks, and mechanical evaluation laboratories. Aberdeen had tested captured German equipment before, including Panzer III and Panzer IV tanks from North Africa, but the Tiger represented something entirely different. The captured Tiger arrived at Aberdeen in early August 1943. Engineers from the Ordnance Department, assisted by technical specialists from the Armored Force Board, began systematic evaluation. The testing program would encompass every aspect of the Tiger's design, from armor protection to automotive performance. The goal was not just to understand German capabilities, but to identify specific weaknesses that could be exploited tactically and to inform American tank development. The first phase focused on armor testing. Engineers measured armor thickness at multiple locations using precision calipers. Frontal hull armor measured 102 mm, turret front measured 100 mm. Side armor measured 82 mm on both hull and turret. Rear armor measured 82 mm. These measurements confirmed intelligence reports and revealed that German armor quality remained high despite increasing material shortages. Metallurgical analysis of armor samples showed proper heat treatment and adequate hardness. Ballistic testing followed. American engineers fired various weapons at captured armor plates to determine penetration capabilities. The 37 mm M3 anti-tank gun, standard American infantry anti-tank weapon in 1943, could not penetrate Tiger armor at any range from any angle. The 75 mm M2 gun, mounted in early Sherman tanks, could penetrate Tiger side armor at 500 meters or less, but could not reliably penetrate frontal armor. The 76mm Monet gun, entering production for improved Sherman variants, could penetrate Tiger frontal armor at 500 meters under optimal conditions. The 3-inch M7 gun mounted on tank destroyers could penetrate Tiger frontal armor at 1,000 meters. These test results confirmed what combat reports had indicated. The Tiger's armor provided protection against most American weapons. Tactical doctrine would need to emphasize flanking attacks and concentrated fire from multiple directions. The 88mm gun underwent detailed examination. Engineers measured barrel length at 56 calibers, providing the extended length necessary for high muzzle velocity. The breech mechanism used semi-automatic operation, with the breech opening automatically after firing to eject the spent casing. This increased rate of fire compared to fully manual systems. American engineers test-fired the captured Tiger's gun at Aberdeen's armor test range. Firing against armor plates of various thicknesses at measured distances, they confirmed the gun's devastating penetration capability. At 1,000 meters, the 88mm armor-piercing shell penetrated 140 millimeters of armor. At 2,000 meters, penetration remained sufficient to defeat any American tank. The gun's accuracy impressed American observers. German optics and fire control systems provided exceptional first-hit probability, but the most significant testing focused on automotive performance and mechanical reliability. This was where American engineers would discover the Tiger's fundamental flaw. The testing protocol called for extended road marches to evaluate reliability under sustained operations. Engineers planned to drive the Tiger across Aberdeen's road test course repeatedly, documenting fuel consumption, maintenance requirements, and any mechanical problems that developed. The first road march began in mid-August 1943. American drivers, trained in Tiger operation by studying captured German manuals, began a 100-kilometer test drive. The route followed paved roads within Aberdeen Proving Ground, simulating road march conditions. Engineers monitored engine temperature, oil pressure, transmission behavior, and overall performance. For the first 50 kilometers, the Tiger performed well. The Maybach engine ran smoothly. The transmission shifted cleanly through all 8 forward gears. Track tension remained proper. No problems appeared. At approximately 70 kilometers, the transmission began making unusual noises. A grinding sound during gear changes suggested something was wrong internally. The test driver reported difficulty engaging certain gears. Engineers documented the problem and ordered the driver to continue at reduced speed. By 90 kilometers, the transmission problems had worsened significantly. Gear changes became increasingly difficult. Some gears could not be engaged at all. The grinding noise intensified. Engineers ordered the test stopped at 95 kilometers. The Tiger was driven back to the maintenance facility at reduced speed in 4th gear, unable to shift properly. Inspection revealed that the transmission synchronizers had worn excessively. The brass synchronizer rings that allowed smooth gear engagement showed severe scoring and material loss. Several gear teeth on the main transmission gears showed stress cracks. Bearings in the transmission case showed excessive wear. After less than 100 kilometers of operation on paved roads under ideal conditions, the Tiger's transmission was exhibiting serious mechanical problems. American engineers were shocked. They had expected German equipment to be well engineered and reliable. The Tiger looked impressive. Its armor was thick. Its gun was powerful. Its overall construction appeared solid. Yet the transmission was failing after minimal operation. German crews in combat would need to cover hundreds of kilometers during campaigns. If the transmission could not survive 100 kilometers on paved roads, how could it possibly survive sustained combat operations? The engineering team at Aberdeen ordered a complete transmission removal and overhaul. Mechanics dismantled the Maybach gearbox, documenting every component's condition. What they found revealed the fundamental design flaw. The transmission was not adequately engineered for the Tiger's weight and operational demands. The gear teeth were experiencing loads beyond their design capacity. The synchronizers were too small and wore out rapidly. The bearings were marginal for the sustained torque loads. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German engineers had essentially taken a transmission designed for a 30-ton tank and scaled it up for a 54-ton vehicle, but had not proportionally strengthened all components. Some parts were stronger, but critical elements like synchronizers and certain bearings remained undersized for the actual loads they experienced. This was a fundamental engineering error that no amount of careful operation could overcome. After rebuilding the Temers and transmission with spare parts captured along with the tank, American engineers resumed testing. The second road march covered 80 kilometers before transmission problems reappeared. The third march lasted 120 kilometers. The fourth march reached 200 kilometers before requiring transmission work. Over 6 months of testing from August 1943 through January 1944, Aberdeen engineers documented consistent transmission failures averaging every 250 to 300 kilometers of operation. This was catastrophic. German doctrine called for Tigers to advance during offensive operations, then withdraw to defensive positions. A typical offensive operation might require advancing 50 to 100 kilometers, engaging enemy forces, then withdrawing. Tigers would need to operate for days or weeks without returning to rear area maintenance facilities. Transmission failures every 300 kilometers made sustained operations impossible. Every Tiger battalion would need to dedicate enormous resources to transmission replacement and repair. The fuel consumption testing revealed additional problems. Aberdeen engineers measured actual fuel consumption during various operations. Road march consumption averaged 4.2 litres per kilometre, higher than German specifications claimed. Cross-country movement consumed 7.5 litres per kilometre. Combat operations with frequent acceleration, manoeuvring, and high power demands consumed 8 litres per kilometre or more. The Tiger's 540-litre fuel capacity provided barely 120 kilometres of road range under ideal conditions. Combat range was less than 80 kilometers. American engineers compared these figures to Sherman performance. A Sherman carried 660 liters of fuel and consumed approximately 0.8 liters per kilometer on roads. Road range exceeded 800 kilometers. Even accounting for combat consumption increases, Sherman range remained 3 to 4 times greater than Tiger range. This meant Tigers required constant refueling. Every Tiger battalion needed extensive logistic support just to keep tanks mobile. The cooling system proved inadequate for sustained operations in high ambient temperatures. Aberdeen conducted tests in summer heat, operating the Tiger at high power output for extended periods. Engine temperatures climbed rapidly. The radiator could not dissipate heat fast enough. Coolant temperatures exceeded safe limits. Under desert conditions similar to Tunisia, the cooling system would be overwhelmed quickly. This explained reports from North Africa of Tigers experiencing engine overheating. The track system exhibited its own problems. The Tiger used interleaved road wheels, with overlapping wheels providing superior weight distribution and ground pressure reduction. This design worked well, in theory. In practice, mud accumulated between the overlapping wheels. In winter conditions, mud froze solid overnight, immobilizing the tank until crews could chip away ice or wait for temperatures to rise. American engineers tested this by deliberately driving through muddy terrain, then hosing down the suspension and allowing it to freeze overnight. The next morning, the tracks were locked solid. Maintenance requirements vastly exceeded those of American tanks. Changing an inner road wheel on the Tiger required removing up to 8 outer wheels first. This could take an entire day with proper tools and trained mechanics. Sherman road wheels could be changed individually in less than an hour. Track replacement on the Tiger required specialized equipment and multiple personnel. Sherman tracks could be repaired by the crew using basic tools. Every maintenance task on the Tiger was more complex, more time-consuming, and required more specialized knowledge than equivalent tasks on American tanks. The Aberdeen testing program produced detailed technical reports that circulated through Army Ordnance and Armored Force channels. Intelligence Bulletin No. 79, published in December 1943, contained comprehensive Tiger technical data. The bulletin noted the Tiger's impressive armor and firepower, but emphasized the vehicle's mechanical weaknesses. Transmission reliability was specifically highlighted as a critical vulnerability. Tactical recommendations based on Aberdeen testing emphasized avoiding frontal engagements. American tank commanders were advised to use terrain and maneuver to attack Tigers from the side or rear where armor was thinner. Artillery was recommended as the most effective counter to Tigers. Infantry anti-tank tactics should focus on close assault with satchel charges or bazookas targeting vulnerable points. Most importantly, tactical bulletins noted that Tigers had limited operational range and would frequently be out of fuel or broken down. Forcing Tigers to move long distances would stress their mechanical systems and increase breakdown probability. British forces conducted parallel testing of captured Tigers. In September 1943, British 8th Army captured Tiger 131 near Tunis. This Tiger was shipped to the United Kingdom for evaluation at the Fighting Vehicles Proving Establishment in Chobham. British testing reached similar conclusions to American findings. The transmission was the Tiger's weakest point. British engineers documented gearbox failures after approximately 250 kilometers average operation. British reports noted that the Tiger was mechanically unreliable and unsuitable for sustained operations. Soviet forces captured numerous Tigers on the Eastern Front and conducted their own testing at the Kubinka proving ground near Moscow. Soviet technical analysis reached identical conclusions. The transmission was inadequate for the Tiger's weight. Mechanical reliability was poor. Fuel consumption was excessive. Soviet engineers calculated that Tigers required 3 times the logistics support of 34 tanks to achieve equivalent operational effectiveness. The intelligence sharing among Allied nations meant that by early 1944, American, British, and Soviet forces all understood the Tiger's weaknesses. The psychological impact shifted dramatically. In early 1943, the Tiger had been feared as an invincible superweapon. By mid-1944, Allied tankers understood that Tigers were dangerous but mechanically fragile. The fear remained. Tigers could destroy Allied tanks easily in direct combat, but the myth of invincibility was shattered. German crews experienced the opposite psychological journey. Initially confident in their invincible Tigers, they quickly learned that their tanks were unreliable. Transmission failures became routine. Every long march meant inevitable breakdowns. German tank commanders knew their Tigers might fail mechanically at any moment, leaving them stranded deep in enemy territory. This knowledge created caution that undermined aggressive tactics German doctrine required. The transmission problem stemmed from multiple factors beyond simple design inadequacy. German steel quality began declining in 1943 as the Reich lost access to critical alloying elements. Molybdenum, which increases steel's resistance to heat and fatigue, became scarce after Allied bombing eliminated German access to Norwegian sources. Nickel, another critical alloying element, grew increasingly scarce. Transmission gears made from lower quality steel wore faster and failed sooner than properly alloyed components would have. Manufacturing quality also declined as Germany faced labor shortages. Skilled machinists were conscripted for military service. Replacement workers included forced laborers and concentration camp prisoners who had neither training nor motivation to produce quality work. Tolerances slipped, assembly quality declined. Transmission components that should have been precisely manufactured were increasingly crude. These manufacturing defects compounded design inadequacies to produce catastrophic reliability problems. The production statistics reveal Germany's strategic error in Tiger deployment. Germany produced approximately 1,500 Tigers between August 1942 and August 1944. Peak production reached 104 units per month in April 1944. Each Tiger consumed industrial resources equivalent to 3 Panzer IV medium tanks. The man-hours required to build one Tiger could produce 4 Sturmgeschütz assault guns. For the resources invested in 1,500 Tigers, Germany could have produced 6,000 reliable Panzer IVs. The United States produced 49,324 Sherman tanks between February 1942 and July 1945. Soviet Union produced 57,734 tanks during the war. Britain produced approximately 27,000 tanks of various types. The combined Allied tank production exceeded 130,000 vehicles. Germany's 1,500 Tigers represented slightly more than 1% of Allied tank production. Even if every Tiger had been perfectly reliable, the numerical disparity would have been overwhelming. But Tigers were not reliable. The 50 to 60% operational availability rate meant that of 1,500 Tigers produced, only 750 to 900 were actually available for combat at any given time. Accounting for training units, tanks in transit, and vehicles undergoing depot-level maintenance, perhaps 500 Tigers were actively engaging Allied forces across all fronts. This represented approximately 0.4% of Allied tank strength. German investment in Tigers made no strategic sense. The human cost of German engineering choices extended beyond simple production numbers. Tiger crews required extensive specialized training. The transmission was complex and demanded skilled operation. The engine required careful management. The weapons systems needed expert handling. Training a Tiger crew took 3 months. Training a Sherman crew took 6 weeks. Germany could not afford the time or resources for extended crew training by 1944. Tiger crew casualties from mechanical failures were proportionally higher than casualties in more reliable tanks. When transmissions failed under fire, crews could not retreat. When engines seized during combat, crews were trapped in disabled vehicles while enemy forces closed in. German records document numerous instances of Tiger crews killed or captured because mechanical failure prevented escape from damaged vehicles. The tanks that were supposed to protect their crews instead became steel coffins when mechanical systems failed at critical moments. The operational impact of Tiger unreliability shaped German defensive strategy during 1944. German commanders knew Tigers could not conduct sustained mobile operations. Offensive maneuvers requiring long advances were impossible because Tigers would break down before reaching objectives. This knowledge forced defensive tactics that surrendered initiative to Allied forces. Tigers were positioned in prepared defensive positions, where they could engage advancing Allied tanks from static locations. This negated the Tigers' mobility advantages and allowed Allied forces to dictate the tempo of operations. The Battle of Normandy in summer 1944 demonstrated these problems at operational scale. Germany deployed approximately 120 Tigers to Normandy between June and August 1944. These Tigers were distributed among several Schwerpanzer-Abteilungen attached to various infantry and panzer divisions. The Tigers achieved tactical successes in individual engagements, destroying numerous Sherman tanks from defensive positions. But operational availability never exceeded 60%. Mechanical breakdowns constantly reduced combat strength. Recovery operations consumed resources desperately needed elsewhere. American forces, advancing through Normandy, frequently encountered abandoned Tigers. After-action reports document finding Tigers beside roads with transmission failures, engine problems, or simply out of fuel. Some had minor damage that would have been easily repaired in more reliable vehicles, but the Tiger's complexity made field repairs impossible without specialized equipment. German recovery units lacked heavy equipment to tow 54-ton tanks. Disabled Tigers were often destroyed by their crews to prevent capture. The Falaise pocket encirclement in August 1944 trapped numerous German units, including several Tiger battalions. As German forces attempted to escape the pocket, Tigers broke down at catastrophic rates. The stress of sustained movement, combat operations, and fuel shortages caused transmission failures across entire units. German forces abandoned dozens of Tigers during the retreat. Post-battle surveys found more Tigers abandoned due to mechanical failure than destroyed by Allied fire. This pattern repeated during the retreat across France. Tigers that survived combat were lost to mechanical breakdowns. The Battle of the Bulge in December 1944 provided the final demonstration of Tiger unreliability under operational conditions. Germany committed approximately 70 Tigers to the Ardennes offensive, distributed among several Schwer Panzerabteilungen. The offensive plan required rapid advances to seize bridges over the Meuse River. Tigers were expected to provide breakthrough capability and mobile firepower. Within 1 week, mechanical failures had reduced Tiger strength by approximately 40%. Transmissions failed during the advance, engines overheated, cooling systems leaked, fuel consumption exceeded planning estimates. Tigers abandoned for mechanical reasons littered the roads through the Ardennes. American forces advancing after the German offensive stalled found dozens of intact Tigers, many with only minor mechanical problems. German recovery units could not retrieve disabled tanks before American forces recaptured territory. The offensive failed not primarily from fuel shortages, as popular accounts suggest, but from systemic unreliability of German armoured vehicles that limited operational tempo even when fuel was available. The contrast between German and American approaches to armoured vehicle design reflected fundamentally different philosophies. German military culture emphasized technical excellence and engineering sophistication. German engineers designed weapons for ideal conditions, assuming proper maintenance by trained technicians using specialized tools in well-equipped facilities. This approach produced impressive specifications, but poor reliability under field conditions. American military culture emphasized practicality and operational sustainability. American engineers designed weapons for realistic conditions, assuming field maintenance by minimally trained personnel using basic tools under combat stress. The Sherman tank exemplified American design philosophy. It was not the best tank by any specification. Its armor was adequate, not exceptional. Its gun was competent, not outstanding. Its speed was acceptable, not remarkable. But the Sherman was supremely reliable. Its engine rarely failed. Its transmission could survive abuse. Its suspension withstood punishment. Maintenance was straightforward and could be performed by the crew with basic tools. These virtues, dismissed by German engineers as evidence of technical inferiority, proved decisive. The final accounting reveals the magnitude of Germany's strategic error. 1. 1,500 Tigers hamstrung by mechanical unreliability achieved operational effectiveness roughly equivalent to 750 reliable tanks. The resources consumed by Tiger production could have produced 6,000 Panzer IV tanks. 6,000 reliable Panzer IVs actually available for combat would have provided far greater military value than 1,500 temperamental Tigers. This conclusion is not speculation but mathematical certainty derived from operational availability statistics and production cost analysis. The lessons learned from Tiger testing influenced every American armored vehicle designed after World War II. The M26 Pershing heavy tank entering service in 1945 incorporated extensive reliability testing before deployment. The M46 Patton tank entering service in 1949 emphasized mechanical reliability equal to combat capability. The M48 tank entering service in 1952 made reliability and maintainability primary design requirements. The M60 tank and Moni Abrams tank continued this emphasis. Modern American armored vehicles trace their design philosophy directly to lessons learned from examining German mechanical failures. Universities teaching engineering management use the Tiger I as a case study in how complex systems fail when design requirements exceed engineering capabilities. Business schools study the Tiger as an example of how organizational culture can produce catastrophic strategic errors. The Tiger looked magnificent. Its specifications were impressive. Its combat performance in ideal conditions was exceptional, but it failed the only test that mattered. It could not be sustained in combat operations long enough to affect the war's outcome. The Aberdeen Proving Ground testing program produced one additional finding that received less attention but carried profound implications. American engineers calculated the total cost of fielding one Tiger for 1 year of operations. This calculation included not just production cost but also fuel consumption, spare parts, maintenance personnel, recovery equipment, and logistics support. The total came to approximately 450,000 Reichsmarks per Tiger per year. For comparison, fielding one Sherman for 1 year cost approximately $85,000, equivalent to roughly 200,000 Reichsmarks at wartime exchange rates. Germany was spending more than twice as much per tank to field less capable vehicles. The economic arithmetic was devastating. Germany was losing the industrial war before the first shot was fired. The Tiger represented Germany's response to this reality, an attempt to overcome numerical inferiority through technical superiority. The strategy failed because technical superiority without mechanical reliability and logistical sustainability means nothing in sustained industrial warfare. The captured Tiger tested at Aberdeen remained at the proving ground for years after the war. It was displayed outdoors as a memorial and training aid. Decades of exposure to weather gradually deteriorated the vehicle's condition. In the 1970s, the Tiger was moved to the Aberdeen Proving Ground Ordnance Museum for indoor display. Further restoration occurred in the 1990s. The tank remains on display today as the only Tiger I in the United States captured during World War II and tested by American engineers. The technical reports produced from Aberdeen testing influenced not just American tank development, but also broader military procurement philosophy. The principle that operational availability matters more than theoretical capability became foundational to American defense planning. Weapons that work reliably under field conditions defeat weapons with superior specifications that cannot be maintained. This principle informed development of aircraft, artillery, small arms, and every category of military equipment designed after 1945. The German tank crews who fought in Tigers experienced a unique psychological burden. They had been promised invincibility. They had been told their tanks were technically superior to anything the Allies fielded. They had been assured that German engineering excellence would guarantee victory. Then they experienced the reality. Their tanks broke down constantly. Transmissions failed at the worst possible moments. Engines overheated during critical operations. Fuel ran out far from supply points. Recovery was often impossible. The gap between propaganda and reality demoralized even veteran crews who had survived years of combat on the Eastern Front. For American tankers who studied intelligence bulletins based on Aberdeen testing, the evolution in understanding was equally dramatic. In early 1943, the Tiger inspired terror. By late 1944, American crews understood the Tiger was dangerous, but fragile. The fear never entirely disappeared. A Tiger could still destroy a Sherman in direct combat, but the psychological impact shifted from panic to respectful caution. American tankers learned to exploit Tiger weaknesses, force them to move, attack from multiple directions, use artillery to disable them, wait for mechanical failure. These tactics, informed by systematic intelligence analysis, reduced American casualties and accelerated German defeat. The broader strategic lesson extends beyond tank design to encompass fundamental questions about military effectiveness. What makes a weapon effective? Is it the thickness of its armor, the power of its gun, the sophistication of its engineering, or is effectiveness measured by operational availability, logistical sustainability, and actual presence on the battlefield when needed? The Tiger I answered these questions definitively. A magnificent tank that spent more time broken down than fighting was less effective than an adequate tank that was actually present for combat. Modern military planners continue to reference Tiger I reliability problems when evaluating new weapons systems. The question asked during every development program is simple. Will this system be reliable enough to sustain operations under field conditions? If the answer is uncertain, the program faces skepticism regardless of impressive specifications. This skepticism, born from World War II experience analyzing German mechanical failures, has prevented numerous procurement disasters and shaped American military effectiveness for 80 years. The Tiger I remains famous today, featured prominently in documentaries, films, and popular culture as Germany's most fearsome tank. That reputation is partially deserved. In direct combat under favorable conditions, the Tiger was genuinely formidable. British tank commander Patrick Delaforce, who fought in Normandy, described encountering a Tiger as terrifying. The massive size, thick armor, and powerful gun combined to create a weapon that dominated any engagement where it could be brought to bear effectively. But that scenario represented perhaps 20% of actual Tiger operations. The much more common scenario was the one documented by Aberdeen engineers in their testing program: long marches causing transmission stress, sustained operations exceeding cooling system capacity, fuel consumption outpacing logistics support, inevitable mechanical failure far from maintenance facilities, component wear exceeding replacement part availability. Of 1,500 Tigers produced, the vast majority were lost to mechanical failure, fuel exhaustion, or abandonment rather than combat destruction. The American engineers who tested the captured Tiger at Aberdeen Proving Ground took away lessons that shaped military procurement for generations. They learned that impressive specifications mean nothing without reliability. They discovered that sophisticated engineering without adequate testing produces weapons that fail. They understood that logistical sustainability determines what is operationally possible more than raw combat capability. These lessons, purchased at terrible cost in American lives during early encounters with Tigers in Tunisia, saved countless additional lives in subsequent engagements across Europe. The final irony is that Germany knew about the Tiger's transmission problems, but could not fix them. German engineers understood the gearbox was inadequate. Henschel proposed upgraded transmission designs with stronger components, but Germany lacked the industrial capacity to implement improvements while maintaining production rates. Stopping production to redesign the transmission would have reduced available Tigers even further. Continuing production with known flaws meant deploying tanks that would fail mechanically. Germany chose to continue production, accepting catastrophic reliability as the price of fielding any Tigers at all. This choice reflected Germany's strategic situation by 1943. Facing overwhelming Allied industrial capacity, losing access to critical raw materials, suffering from skilled labor shortages, and fighting on multiple fronts, Germany had no good options. The Tiger represented an attempt to compensate for numerical inferiority through technical superiority. The attempt failed because technical superiority without mechanical reliability cannot be sustained in industrial warfare. The war would be won by the nation that could field reliable tanks in overwhelming numbers, not by the nation that built magnificent tanks that broke down. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.